All right, how's everybody doing? Sorry it took so long to get started. It was a headache. At least after this class, we don't have to worry about the Wi-Fi for a few weeks. All right, we're talking about soil sensing a little bit. What I'm going to be going over for that first half is all conceptual. These are some things that you'll come across if you work in the geotechnical engineering field or you work with geotechs. Some of the equipment that we use aside from subsurface testing. And then we're going to do the exam review. So last lecture for geotech. So yeah, some updates. Again, lab 9 is still on the table. Still need to get those completed. I will post, and I did see your email, so I will post the video on how to do the Google Earth like stuff from the CE materials lab. I know not everyone's familiar with Google Earth. So if you have any specific questions with that, feel free to reach out, but I will have a video on Canvas here after class that goes over how to take the image from Google Earth and make a map and all that fancy stuff. If you don't know by now, hopefully you do, May 5th is our exam, so 1 week from today. And again, it's at 7 a.m. And again, I'm sorry, but just practice waking up early and using your brain, you know, in this week that we still have. If you haven't already, complete the ISQs, please. There's a lab in the lecture section. Last time I checked, it was at like 55% of the class completing it. So right now, that means there will be 5.5 points worth of extra credit on the final. So the more people that fill that out, the higher extra credit questions, all that fun stuff. So yeah, any questions on where we're at? Wrapping up the class. Cool. Oh yeah, what's up, Christian? Yeah, so actually I did post some. I didn't make an announcement, so I'm sorry about that. Good point. Yeah, there are exam practice problems posted on Canvas. So in the lecture notes side, if you scroll to the very bottom in the week that we're at, you'll see the PDF there. I'm not going to get time to go over those in like this class today, but I will post the solutions over the weekend. And I might do a video explaining it both ways. So if you want to just review the PDF of the solutions, you can do that. And I'll also have a video explaining the step-by-step for that. We will do some example problems today, but I haven't posted them ahead of time. So just go over these and then review them on your own. All right, so what we've been talking about this whole time over the past couple of weeks, we've been talking about stresses in soil and the importance of that moving forward in geotechnical engineering design. So we know if we have a subsurface profile, let's just say we have this point here, and this whole thing is just a sandy soil, we can do different tests like the sand cone test, CPTs, SPTs, different types of subsurface investigation tests to determine what type of material this is, and we can also determine the unit weight of the material, right? So as we go deeper in depth, like at this point A, for example, we know that there is something called an in situ stress being felt at this point. We note this as delta sigma V. So, or sorry, sigma V 0. So what this is our initial vertical total stress. So we're just looking at total stress here, but again, if we subtract out the pore water pressure, then we get our effective stress. But just looking at total stress, what we've been talking about so far is if we include some type of structural loading or something on the surface that has a finite geometry, this stress we'll call Q. This is from like structural loading or something like that. And what we know is that that stress will decrease in value with depth, so it'll dissipate with depth. But at this point A, we'll still feel this increase of stress, and we call that increase our delta sigma V because it's vertical. So our delta sigma, delta is the change or the increase in stress. V is for vertical. So that means if we have our initial and we add our delta sigma V. Then what we have is a new stress, right? We have deltas, or we just have sigma V. So again, talking about the subscripts, sigma V0, or what's sometimes called sigma V naught, that's the initial. So not, you could picture that as like a timestamp, like 0 or something, you know, like this is the initial like condition. Once we add something, we have our now new condition, which is just our sigma V. So this is our new stress. As you can imagine, this new stress is something that we need to consider as geotechnical engineers. So the increase of stress, which we've talked about this past couple of weeks, the past couple lectures, this is that increase. So we found the different ways of estimating this. So this is always estimated. And we talked about the different techniques in the past couple lectures. What were some of the techniques? Who remembers them? There was one that was 2 numbers, 2 to 1 method. Right, there's another one that was all those fun tables and stuff. That is Businesque. I feel like I spell the guy's name different each time. This assumes elastic material. Then a guy named Newmark came and made cool looking, like trippy looking charts based off of the Businesque. So we have Newmark's charts. And then something we haven't touched on in this class are the numerical models. So different types of finite element. Finite element modeling, which is called FEM. It's sometimes just called in the broad category of finite element or numerical modeling, which is basically a fancy way of using computers to solve a bunch of equations at the same time to simulate loading conditions and how the soil is going to respond to that. So what we see with all of these right here, these are all estimates, right? I've talked about that in all of these, like for the past couple lectures that we've been going over. This is good techniques for estimating, or if you need to find the increase of strength for low or low critical infrastructure. Sorry, that says infrastructure. So like if you're designing something that you have a high confidence about, you know, like I've used like the Wawas or like almost like the cookie cutter designs where the soil conditions or the site conditions are well known. You have high confidence as an engineer that the site conditions are represented by your analysis, and this increase of stress that you're estimating in the soil layer, you know, if you're off by 100 PSF or, you know, if you're off by a little bit, it's not going to be a big deal for the life or the comprehension of the whole project. But some projects, of course, require a little bit more confidence, right? What they would require is actual in situ sensing. So what does in situ mean again? This fancy word? In place, yeah. So actually monitoring and sensing the ground conditions in situ. So the point that we care about. So instead of estimating at point A right here and using these fun equations in math to try to understand what the stress conditions are out down there, there's going to be some projects, and hopefully, you know, if you're working on these projects, that means you're getting paid more money. So hopefully you guys get a chance to work on these, but some of them will actually require installation of sensors and equipment that will physically measure the loading and stress conditions at that depth. So some require in situ sensing, then monitoring over time, and analyzing. of actual stress. So this is really important for, high critical infrastructure projects, but also for problematic soils. So like soil that we are not confident about. What is an example of problematic soil in Florida? Who remembers what we've been talking about? Organics, yeah. Yeah, so if you're working in Florida and you're in geotech and you come across a site that has a lot of organics, like something that looks like this, it's kind of hard to see. But just the way Florida was formed geologically, the landmass of Florida, we have cases where you're not going to be able to see this on the screen, but if you look at the video again, you'll probably see that we have levels of high organics in soil layers that are pretty deep. So this soil layer is 5, 10, 15, so about 20 feet down in depth. We have organic soils with 28% organic content. Same down here. So about 5, 10, 15, so 16 feet in depth. We have this 10-foot layer of organics. This one's even worse. We have this soil layer down here that's about 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60 feet in depth. You have this thick layer of organics, dark brown, sandy muck and stuff. And this is something that, in Florida, we come across a lot just because of the landmass, how it was formed geologically. And the fact that all Florida used to be, a swamp a long time ago. So as we mentioned before, like organics are a big headache. And if they're at the surface, we usually just remove them entirely. 60 feet down, how are we going to remove these soils, this soil layer? We can't dig a 60-foot excavation and then, suck them out. So what we actually do is we actually use this delta sigma Z, this increase of stress, to our advantage. And a type of project that if you work in Florida long enough, you'll probably come across are called roadway surcharges or surcharges in general. And this is a really good example of a case where we need to do actual measurements and actual sensing of in situ conditions. And we can't just rely on the 2-to-1 method in the Boussinesq equation and stuff. So Florida surcharges are kind of unique because it's a workaround where we actually will be using this delta sigma Z, so this increase of stress at a certain layer, to our advantage. And we do that to compress or consolidate undesirable soils. And we haven't really introduced this term consolidate before. But consolidation basically just means the change in volume due to the dissipation of pore water pressure. So if we have like a water balloon, like that's sealed, and you push on the water balloon, nothing's going to change, right? The volume, it may like change in shape, but it's not going to change in volume. It's not going to decrease in volume. Now, if you poke a bunch of little tiny holes in it, like just like really small holes, like not, like a little safety pin, and you try to squeeze that water balloon, then water is going to escape, but very slowly, right? There'll be like these little spurts coming out. So you can push, and you can push, but it's only going to change in volume, like based off of time. So the longer you push on it, the more time it's going to take to, or the more volume it's going to decrease in. So soil is kind of the same way in low permeable soils. If you can picture that water balloon like a big chunk of clay, the pore space in that clay is so small that it has such a low permeability that if we squeeze it for a really long time, then eventually it's going to change in volume. So that squeezing is basically that delta sigma Z that we need to use. So we see that in organic soils and we see that in clay soils, and that's what that term consolidate means. So consolidates organic and clays. If you take the foundations class with me, we'll get into a long, much more in-depth discussion on consolidation. But basically, if we can strategically change the soil, or if we can strategically place the soil fill at a site such that we cause a large increase in stress, a large delta sigma Z, then we can accelerate this whole condition of decompressing the soil, or of compressing the soil that is undesirable before we put a critical infrastructure on it or something. So this happens a lot in Florida, and you may have seen these things and not even realize what was going on, especially for roadway in Orlando, if you've driven in Orlando recently. But like I have like some screenshots of the Wekiva Parkway project where they actually used these soil surcharges. So basically what you don't see here is there's this really old like lake right here, and the lake used to actually come over here. So this all used to be lake and marsh water. But then in like the 40s, before you had to do permits or anything, they just put a roadway over it and forgot about it. So under this roadway are these layers of organics from the lake. And now they need to put this super tall highway in this area. So they came across all these soil conditions. They decided to use a surcharge. So right now, here, I'm going to go through some pictures. Just notice this and like this. You know, those are the two things that are staying the same in the picture. So this is in 2018 pre-construction. What you start seeing is them putting this massive mound of earth here. You know, it basically looks like a little mountain. They try to put like green stuff over it so you don't notice that it's just a giant mound of dirt and when you're driving by it. But what you'll see is that this is actually taller than the roadway is planned. So they need to bring in fill to this project site anyway. So what they do is they concentrate it on this area that has organics. So then they can do the rest of their site prep. You know, they can compact, they can start moving and like utilities around and stuff. And eventually then they use that fill to create the entire roadway. So then you see, you know, them starting to build the stuff that actually looks like it with the MSC walls and all that stuff. So if we were to look at just like a cross section of what is actually happening here, again, if we have this layer of organic soil here and we need to put a roadway on this roadway is going to have an embankment. It's going to have live loads from the traffic, which means it's going to cause some type of increase of stress from this live load and from this embankment at this organic layer, right? So we're going to have some delta sigma Z at this organic layer. This delta sigma Z, again, if on the organics due to this loading, is going to cause a settlement. It's going to cause change in volume. It's going to cause, you know, delta V, change in volume, a settlement. And if we already have our roadway installed there, then that's bad, right? Because the whole thing will be like sinking down. You've probably been on some roads where you see these big dips and stuff, and that's, you know, a settlement that is an issue, because if we need to fix it, then we need to stop traffic. We need to like tear up the road and do all this stuff that costs a lot of money. So instead of having this settlement occur over time, do this little loading, what instead we do is we install a massive embankment. So this is our surcharge. This massive embankment still causes a delta sigma Z here. But now this delta sigma Z is much greater than our original delta sigma Z if we were to just use, you know, install the roadway right off the bat. So this is a much, much larger H. And remember last lecture, we talked about how to calculate the delta sigma Z due to a trapezoidal embankment like this. So you can see how they use it a lot. So this causes an increase in loading. So this delta sigma Z, which then accelerates the settlement. So it takes the time aspect out of it. So this accelerated settlement is occurring before we put a super expensive roadway and we have public driving on it, right? So it's kind of nice. Like, and then if we need to bring the soil anyways, we can then move this heavy mountain of soil over to the areas that aren't settling, and we can actually carve our original elevations out of that. So this is super important, but if we were just relying on Boussinesques and if we were just relying on the 2-to-1 method, then, you know, we might not be able to capture, like fully capture what is is happening in situ in this state. So for projects like this, the stress always needs to be monitored. There's a lot of monitoring, and not only like little snap, like once before the project and after project, but over time as well. So we're going to talk about all those things. So again, what is basically happening is, just because I like to use PowerPoint and draw little animations. So we are compressing that organic layer, and then from that we can then change, use that surcharge to fill in to bring that up to grade elevation, and then put our cars back on it. And now hopefully whatever settlement was going to occur in 10 years or so, we've caused to occur right off the bat, and this road won't, settle in the future. Yeah.
How long does that stand there for? Like a year?
It depends. That's one of the design things. So the function of permeability that we talked about, the rate at which water leaves, there's something very similar to that called the coefficient of consolidation, where they'll actually do these tests and determine at how long it takes for soil to compress. So the time aspect of permeability. So they would do that test, and then based off of the height of it and the other soil conditions, they could, find an exact time. But the project I just showed was, I think it was only for a year, because it wasn't too bad. I worked on one project in Orlando too that was like a 2-year monitoring. And it depends on how critical the road was too. So what they actually did for that project, they just diverted the road away from it temporarily, and then have this surcharge here. So, the traffic was okay. They weren't in a time constraint, but for a project like this, where, time is money, they had to accelerate it through some ways. So yeah, a lot of these very popular in Florida where there's organics. I don't know in Jacksonville, especially this side of St. John's, it's probably not that big of a deal. But if you drive in Orlando, have any projects in Polk County, or even, Gainesville area where we have these organic layers, this is a really common technique. So what you'll see is if you work on any of these projects, there's a lot of in situ monitoring. So some of the things that we need to monitor, and these are all the things we've actually talked about in class, is obviously the in situ total stress. All right, so this is our sigma. So we found ways of estimating this using our gamma, right? Estimated gamma values and the heights and the geometry and all that stuff. But we can actually install equipment that can measure this. And the thing that most common is what's called a pressure plate. These all have fun names too, just because contractors work on them. So these are sometimes called pancake plates, and you'll see why in a picture here. What's another thing that we might need to know? If we think about again what a surcharge is doing, it's increasing the pore water pressure, and then it's dissipating over time, like a balloon deflating slowly over time. So what would be another value that we would need to monitor over time? The in situ, how do we find effective stress? Yeah, the pore water pressure, right? So we could measure actually the in situ pore water pressure. Does anyone know what those devices are called? How we measure this, like the pore water pressure inside? May have heard them in some of your other classes. They're called piezometers. Anyone heard that word before in hydraulics or anything? Okay, yeah, so piezometers. It's actually a sensor that we install at depth, and it measures the pore water pressure. So this is perfect. We have ways of measuring our total stress. We have ways of measuring our pore water pressure. So that means we can calculate our effective stress, the actual effective stress, instead of just estimating based off of the estimated other values. There's another thing. If we care about the settlement, then obviously we need to also measure the in situ settlement. And so there's a few techniques that we could use. We could actually sit there with a theodolite, from the surveying classes, and measure and see how fast the whole roadway is settling. But there's also another very interesting technique that uses magnet cells. And these also have a fun name. These are called spider magnets, which if you Google, a bunch of scary pictures of spiders come up. So don't Google that. But this is what we at least call them, and what, like, you know, in the industry, people will call them. And you'll see why they're called spider magnets here in a second. The other thing that we would need to monitor here, again, in situ, is the lateral movement. So a lot of times, soil doesn't always move vertically. If you think about a balloon, again, like if you press on a balloon too fast and the water is not escaping from that water balloon, what direction is it going to go? It's going to want to go horizontally, right? So we need to control the loading so it doesn't push the soil sideways. It doesn't just move these organics sideways. So for that, we use these sensors called inclinometers. That should be one word, inclinometer. And so this is to track any soil or how that soil profile is moving horizontally. And of course, there's lots more too. You know, the whole soil sensing industry is really new. So I mean, people are coming up with all sorts of things like you know, like ways of measuring settlement over a long period of time. They have like a LiDAR and other techniques that you can set up like a, you know, pretty much almost like a light pole that's just shining lasers down and measuring any deflection at a really high precision. But the kind of tried and true ones that you'll come across are pressure plates, piezometers, magnet cells or spider magnets, and then inclinometers. So the pressure plates, who wants to guess what these do? They just measure the pressure. So that's why they're called pancake plates. They look like cast iron skillets, basically. But the issue with these is you have to install it before you start loading things up, right? Now, so you can see here, you usually install a couple of them just to take the average. And all they do is they literally just measure the loading on this plate. So if you want to do horizontal loading, you could do that. You just have to orient it, you know, horizontally. And what this does is directly measures the total stress, which is really nice. The thing that is important though with these is they must be installed perfectly flat. And they must remain that way during construction. So you can see often when they're installing these, they don't just throw them, like chuck them underneath and then start loading soil with the front loader over it. You need to dig a hole underneath it, take your level and make sure that it is perfectly flat and on like a strong base, and then pour soil over it. Because you could think about it, if we are measuring these pressure plates this way, we need the soil to be exactly, or loading 90 degrees at this, you know, like if the pressure plate is tilted at all, then we're not getting a good representation of the actual vertical loading. So these are really popular. There's 3 types that we see of ways of measuring it. There's one called the vibrating wire. Vibrating wire strain gauges are a very common thing, and we'll see this in piezometers as well. It's a really cool technique. It's using, like, thinking back to your mechanics of materials course. We know that material, like how a thermometer works, like with temperature changes, we see a change in length, right? Well, also with pressure changes, we see a change in resonance frequency. So like if we took a guitar string and you know, plucked a guitar string, it would have a certain note at a certain tension. So if there was more pressure and that guitar string was under more tension, then it would have a different frequency. So basically what this does is at a really small scale, there's a little steel or copper or some type of wire that's under tension. And when the pressure changes, it produces a different frequency. So there's these little batteries and a little magnet coil that's attached to it that causes the wire to pretty much be plucked. You know, it's like a little magnet that like turns on and off and plucks the wire. And then we can record that frequency of that wire and correlate it to the pressure that wire is being under pressure. So vibrating wire, that's where it comes from. The other types are bonded resistance. And then others are like hydraulic pressure cells, where it's literally like the inside of this little pancake is filled with either oil or some type of liquid, and we can actually directly measure, you know, the change of pressure in that pancake due to the change in pressure of the cell. So you actually have a transducer. So the benefit of this is, since you see these little wires here coming up, they're fed into a data logger, and we can take measurements, you know, remotely over whatever time frame we want. So if we're loading this thing over, you know, a few hours, then we can actually set it so it'll take a measurement every like 5 minutes, every 30 seconds if we want. You know, we can control the loading rate. And once we set it, we can go to, you know, Bob Evans or Golden Corral and hang out and wait for the data to be collected. And we don't have to sit there on site as long as it has batteries. So this is a really beneficial technique, because once you install it, then, you know, you get all this data and you can measure the total stress over time as everything changes. You have a question?
How long do you load it for?
Yeah, that's it all depends on the site conditions.
Like if loading is effective and the soil actually like starts sinking down, wouldn't this become ineffective over a long period of time? If it needs to remain one.
Yeah, so usually if you're talking about settlement, the whole thing is going to move. So you'll install it at the ground surface, and sometimes you'll even put it on a plate or some type of like, you know, foundation where it's not going to tilt. It's all going to settle uniformly. But yeah, like, so the pressure on top of it could change, but it's, you know, usually it's all dependent on the actual like conditions. Because we did a research project with these where it was just all in one day. You know, we like loaded it and then unloaded it in one day. So we saw the increase and decrease. Some projects, you know, have these pressure cells going over a year, measuring like how the traffic loading is changing as they increase, you know, traffic or something. So depending on the project, that like, you know, they could be there as long as you change the batteries, and, you know, you do like the typical service and make sure that, you know, they're supposed to last for a long time at least. But
Okay, dig them out is like.
yeah, some projects you can dig them out. Normally like the ones that we have exhumed and tried to reuse again, this thing is like all bent up. And it still works, but like it's, you know, it's like, again, if you load it too quickly, then that as long as the pressure plate stays flat, then it's okay. You know, like the whole wires and stuff could get messed up. So these things usually cost like $600 or so, which seems a lot to us, but to like contractors and engineers, they're like, okay, these are, you know, sometimes just considered like expendable, like they use them once and they install them and then that's it.
Have you used asphalt?
Yeah, you probably could use it for asphalt. I don't know what the temperature ranges are for that, but these things would be installed like in the sub base, or like even in, you know, subgrade and maybe in some of the base layers. But what you need to do is that like with these, like they have different types and stuff, but this specific one, you wouldn't want to have like aggregate puncture the plate, you know. So usually you'd want to have a layer of like of fine soil over it so it distributes the stress over everything. But yeah, there's a lot out there. If you want to Google stuff, Geocon produces these, or you could just type in pressure plates and you'll see all the different orientations and like different manufacturers and stuff for these. Okay, so pressure plates, total stress. What we have also for pore water pressure is our piezometers. And actually it's the same thing that is measuring before. We actually use a vibrating wire for most of them, but it measures the pore water pressure directly. So instead now they actually have filters. So we're not letting soil in, but we're only letting the water in instead. So we're holding the soil back and only letting the water touch that vibrating wire. And the same thing as before, you know, we pluck the vibrating wire using like a little magnet that's connected to a cable, which is connected to your data logger. And then we measure that frequency. And if the water pressure is super, super high, then that frequency is going to be really high or really low. I don't remember which way it is. But it'll change and it can be correlated with the pressure that it's under. The important thing to note with these are, they are not technically measuring the groundwater table. GWT, that's groundwater table, just so I don't have to write the whole word out. So for low permeable soils, which are usually the ones we care about here, low permeable soils, like clays and even organics, what we'll see is there is an increase in U when loaded. So U is our pore water pressure. So although over time, if we keep these sensors in the ground long enough, it should equal out to our groundwater table. We should be able to use these to find the groundwater table. But if we install these in situ, meaning they're surrounded by soil, and we increase the stress in that soil, what we'll see is an increase in pore water pressure that is not representative of the groundwater table. Again, think about like if you had a sensor in that balloon filled with water and you push on it, then that sensor is going to have a higher pressure, right? If that balloon is confined and it can't change, we're going to have a higher pressure, and then it'll dissipate as the water is able to leave the pore space. So again, these are primarily used for vibrating wire. Lots of different types, but depending on the types of pressure that you might experience, there's these tipped ones where they can actually be pushed and driven into the ground, which is really nice because then you have less intrusion. You can drill a borehole. You can lower the piezometer down to the bottom and then backfill the borehole. There's different ways of getting these to different depths. But what I want to illustrate here with the pressure is if we were to plot, say we were doing a surcharge over time, and we were to plot the load, so the actual stress applied on the surcharge over time. And let's just say it looks like this, it's flat, 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 and then we slowly increase it like this, and then we level this out. If we actually look at the pore water pressure in this same soil region that we care about and plot that. So I'm just going to say pore water pressure, PWP, pore water pressure, which is U again. What it would actually look like is if it had something like this in our sensor, as soon as we start loading it, we would see a spike. And then over time, we would see it level out to our groundwater table or potentiometric head area. And again, visualize a water balloon. When you apply this pressure, the pressure is going to spike up because the water has nowhere to go. And then over time, it finds that low permeable routes to travel out and dissipate. So these groundwater table measurement, or these piezometers are not measuring that groundwater table. And we see this increase and then the decrease over time. And Tess, your question was how long does it take? This whole rate here is the important part. The rate at which pore water pressure dissipates tells you how long you need to have this loading at a constant. Because once we reach this, this zone of the groundwater table, then usually all the compression has occurred and we can remove the soil that way. So piezometers and pressure plates are two really big things that you'll come across in geotechnical engineering. The other one is the settlements, and these are the magnetic probes, or what are also called spider magnets. Holes. At a target depth, so whatever layer we care about. So if we want to see how we are compressing an organic layer 30 feet down, then we would actually drill a borehole to that depth and install these spider magnets. And there's a picture of one right there, and you can see why they're called spider magnets. They actually have these like little, like almost like safety pin things that like go out and grip the end of the borehole. So when we're installing them, they're actually all compressed in, and you can put it through the borehole. And then whenever you get it to a target depth, you just pull these little rings out, almost like a grenade. You pull a ring out, and then those little things, those little legs under tension expand and grip the edge of it. So they like anchor into the soil layer. What you'll see here, well, it's hard to see. These are hollow. So then what we do is when we have this at a target depth, we use this magnet that has a little identifier on it, and we will drop it through the borehole. And whenever that magnet probe goes through our spider magnet, it'll make a little beep. So we can measure over time how that soil layer is changing with the ground surface elevation. So unfortunately with these though, these are manual measurements, manual point measurements. So unlike the pressure plates and the piezometers, we can't just sit it and forget it. We need the interns to go out in the middle of summer to go with these and take these point measurements over time. So our spacing of data is a little bit greater, depending on how good the intern is. But you can install most of these with depth. So like this little picture here, this is with depth, and you can see you have one here, one here, one here. And you can measure how each layer is settling and compressing with respect to the ground surface. If you then use a theodolite to know the elevation at the ground surface, then you can estimate how it is changing, over the entire elevation of it and stuff. So spider magnets, I've never actually used these in industry, but we use these in research a lot. And I think now they're starting to use them more. It's pretty basic technology, but it works pretty good. All right, the last one are inclinometers. So inclinometers are basically just probes that measure tilt. So how like our iPhones have like the level on it and stuff, like you can see the level in it, or the old-fashioned like bubble levels where you can see how it tilts. These probes, if we know the way that something is tilting, and then we know the depth that it's traveling, then we can actually find the lateral deflection. So if you think about it, tilt. So if I know that I'm traveling at this degree and I'm going 50 feet, then I can measure how far off the track I've actually gone. So tilt plus depth is equal to lateral deflection. So how we actually find these, let's say we have a retaining wall like this, and we're worried that the soil is going to move horizontally from this retaining wall, during the construction stages. So what we would do is we'd actually install a flexible PVC pipe, which is really important. It needs to be flexible. So you would not use like a steel pipe or anything rigid. It'd be like a flexible PVC pipe. And over time, if our worst nightmares come true and we do see lateral deflection in a certain area, then what we would expect is this pipe would actually move with the soil, right? So we would see the PVC pipe bending with soil depth. We usually anchor these in some, bedrock layer or something where the bottom is not going to move. And so if we take these inclinometers and we take the profile, so we drop the inclinometer tube through here and then back up, we can get the profile in its nice straight condition, our initial condition. And then over time, if we start seeing movement, then we can start getting the profile in its deformed position. So what this would actually look like is here. Like this is really common used in excavations near historic structures. So if you're digging a basement right next to like something from World War I, or I don't know, some old structure that we don't have in Florida, they want to make sure that that building is not going to be compromised and not going to move. So they install these and they measure them at critical points in time to make sure that we are not exceeding that threshold of movement laterally. So here you can see like what you actually get is a profile. And you can see what they do here. This is like an example where there's different days. So that, you know, day 2, you have this first profile, day 5, you have another profile, day 11, day 15, and then day 9 and day 15 there too. So it's just a probe. I don't have a really good picture of it. A probe that you install and you lower into the hole and then you pull it back up and it measures the tilt with depth. And then you can plot individual points and you can get that profile that way. So what that means is just like our spider magnets, this is a manual measurement. So somebody's got to go out there and drop this probe through that hole that through the borehole and through the PVC pipe that they created. And that's how you get one data point. You know, you can't like have it go automatically. The other important thing with this is our datum is equal to our ground surface. So this is our 0 mark. So that where we put this ground surface is important. And I'll show some pictures here in a second. Think about it like if some of these projects for settlement, you know, that means our ground surface is going to change. And hopefully our ground surface, our datum is settling. So we need to consider that when we're actually installing these inclinometer tubes, because, you know, our datum could potentially change. They also, these are like, you know, long-term testing. So we need to be installing, and that says installing, not entailing, installing strategically at a project site. Fuzzy. Because again, they're manual measurements. So we need to access the location. One of the projects I was working on was in Sanford, down like, you know, north of Oviedo-ish area. There's a highway that's been settling for like the past 40 years. So they put a surcharge on it. It's an old like swampy area just north of the airport. So they put this beautiful surcharge on it and delayed the traffic, you know, south of it. And, you know, we had to go out every day or twice a week and record settlement, record piezometers. And then we also had inclinometers. You can't really see in this picture, but here is one of those inclinometer tubes, and you can actually see zooming in. It had settled so much, that whole site settled so much, but now to get the inclinometer probe into the top of the tube, it was like 6 feet above us. So we didn't want to change that tube because we knew the elevation of that tube. So what we had to do was somehow, you know, stand on shoulders and get the inclinometer probe at the top because the ground surface had settled so much. Right here. Other issues that we didn't think about when they installed these, right here, this is the tube here too. So that's the top of the tube. And so that's not fun, trying to walk down you know, the side of a surcharge. And, you know, we eventually ended up not taking data because it was too flooded and we couldn't get the equipment down there and it was just too unsafe. So thinking ahead of time, you know, the soil is going to be always like unpredictable and stuff, but you have to like consider some of these long-term monitoring and ensuring that you have the access to it, so you don't send your interns into like water moccasin areas and stuff. So yeah, this project, if you're curious at all, it was State Road 46 surcharge. You could probably find data over it. It was back in like 2018, so I think the road is finished now. But it was really interesting because the traffic was just diverted for 2 years. You know, the public never knew why. They were just like, oh yeah, no, okay, they must be doing road construction. But the whole reason was for this giant surcharge. You could see went the whole way, just to compress the soil so they didn't have to come in once a year and resurface the asphalt from it settling so much. Okay, so those are the 4 things conceptually that you guys might come across. They're not going to be in your PE or it might be in your PE, but they're not going to be in your FE. It's just some interesting stuff that you'll come across if you're working in geotech. Got 15 minutes for exam review real quick. So any questions on sensing or anything like that? I know we kind of got to rush here, but if you have any questions or want any more information, want any of these geotech reports, I'd be happy to send them to you. On any of the FDOT stuff, you know, as long as you pay taxes, it should be free to you, so you can get whatever you want. All right, so the topics for our exam 3, in situ soil stresses. So understanding effective stress, total stress, and pore water pressure is super important. We're looking at being able to calculate that using hydrostatic conditions. So hydrostatic meaning there's no water flow, but also we have to be able to find the effective stress and pore water pressure in upward and downward flow conditions, so seepage effects. So how that changes our pore water pressure, which will then entail change our effective stress, right? We talked about specific examples of heave or quick conditions. So that's when our effective stress is 0. So that, you know, we had a homework problem and example problem like that. Capillary rise, so suction. So when we have negative pore water pressure. And then also horizontal stress. So understanding that horizontal stress is a function of the vertical stress, right? And we use this K naught value, this lateral or horizontal earth pressure coefficient. So we have our in situ soil stresses, and then we also talked about what happens when we load the ground surface and we change that vertical stress. So what we're doing is, increase in vertical stress using Boussinesq's 2-to-1 method. So 2-to-1 method is really important. And then Newmark chart. This how to read should be on Newmark chart. Create and draw a Newmark chart because that requires scaling of the footprint and everything like that. Again, you should be able to at least be able to estimate what that increase of stress is by looking at a Newmark chart. And then conceptually, the soil sensing, that was all stuff. So all conceptual stuff. Interpretation of data and all that stuff, that's just something we wouldn't be able to test on. But if you take the foundations class, then that's something we'll definitely be covering, actually interpretation of that data and that kind of stuff. All right, so I have a few examples I just want to go over just to refresh everybody. This is not like writing in, so if you want to just sit back and like pay attention and make notes, but it's all just going to be through the power of PowerPoint, so I'm not like writing anything in. We have a problem like this. This is a vertical in situ stress. We need to determine the total stress, pore water pressure, and effective stress at these points, so D, C, A, and B. So basically the profile, it's like the problem from our homework where you needed to plot the profile of it. So the first thing you need to do when you see these problems are check and make sure you have the correct unit weights. And what unit weights do we have here? We actually have none. So we need to go back to our fun phase diagram relationships and determine the unit weights, estimate the unit weights for this. And this is really like something that you would need to do in engineering because it's hard to measure the in situ unit weight. We can take a soil and we can find the specific gravity, we can find the void ratio, and we can find all these other index testing, but the in situ unit weight, we can't just directly measure in the lab. So to do that, what we're first going to do is assume hydrostatic and no capillary rise unless it's stated. So, unless it's stated in the problem statement, then we'll assume that. We need to find the unit weights, and we need to make sure that we're choosing the right unit weights here. So if it's below the water table, look for the triangle here. If it's below the water table, then we know we're going to use saturated. If it's above the water table, then we need to check and see what the problem is telling us. So if it says dry sand, that means we're using gamma D. We're using gamma dry, the dry unit weight. If you were given a moisture content here, then we know that we would need to find the moist unit weight or the bulk unit weight. So including the water in the pore space. So below the groundwater table, everything else is saturated, right? So if we're below the groundwater table, then we just assume saturated conditions. So what I'm just going to do is label these 3 layers. And so from the Briard textbook and from my notes and everything, we can find these correlations to determine the dry unit weight and determine the saturated unit weight given what the information we have, right? So for the first soil layer, we have void ratio and specific gravity. We can find those and we can calculate gamma dry for the first layer about 16.8 kilonewtons. In this step, when you're doing this, always double check and like think if these numbers make sense. Like if it's in pounds per square foot, if it's in pounds per cubic foot, it should always be somewhere between like 70 and 120, right? No, 150 is concrete. Having a soil that is more dense than concrete is really, really rare unless it's a rock. And then water is 62.4. So it should always be more dense than water, less dense than concrete. For SI units, density of concrete is about like it's like 27 or 28 kilonewtons per cubic meter. Density of water is 9.81 kilonewtons per cubic meter. So somewhere in between that range is where our soil should be. So that's for the first layer. For the second one, gamma saturated, you can use the same equations. So 20.8, and then for the third one, these are all from our index testing, so which is why I'm on the your little initial sheet. I'll still have that table of all of the phase diagram relationships and stuff. So once we have all these, then we can start our calculation. So we have our unit weights, and now we just need to worry about the heights and stuff. So we'll start at the bottom for our vertical in situ stress, total stress at D. That's just everything that has weight above us. So we have all of our soil conditions. We see that it's about 175 kilopascals at C. All we're doing now is removing this last layer. And then if we work our way up, then obviously we're just slowly removing. And at point A, since there is no surcharge at the surface, so there's nothing here, then we have 0. All right, so straight ahead, everyone's good so far, hopefully. For our pore water pressure, since we're hydrostatic, we're just looking at where the groundwater table is. So pore water pressure is the height of the water. Height of the water at whatever point we care about is just this. Make sure you're using the correct unit weight for whatever units we're in. So 9.81 kilonewtons per cubic meter. At point D, we have this 5-foot layer plus our 1.5-foot layer, or you could just do 6.5 meters. Sorry, meters, not feet. And so we have this here, and then at point C, 1.5. Point D, since we're at the groundwater table, we have no height of water above us, so that's 0 kPa, and obviously at point A, we have 0. And this is what we're given here. So we have our pore water pressure. Now we can calculate our effective stress. So effective stress is always total stress minus pore water pressure. Don't forget this little guy here. Effective should be that. It's really easy to, when you're in a rush, to switch those around and think total stress is effective stress minus pore water pressure. But the apostrophe is on the left. So we can calculate our effective stress, and we have all the information. So now let's see this problem and assume capillary rise occurs for 1.5 meters above the water table. And let's say that degree of saturation in the capillary zone is 100%. So for this problem now, we do not have a complete dry sand. And let's just say that this is a silt, since capillary rise mainly occurs in fine grained soils. So this would mean the problem would probably have something that looks like this. We would have these little tentacles looking up, and that's just to show that water is rising up above our water table, where our groundwater table is. So this means we would actually need to find our saturated density in this layer. So to do that, we would go through and find our gamma saturated, and then we can find this to be about 20.3 kilonewtons per cubic meter. Now, as soon as we get above this point, we're back to dry sand. So everything else is the same. So with this one, since it's stated that we have capillary rise, then we would assume that there is capillary rise. So for total stress, everything at the bottom is the same, except we have a different density. So here, I should point here. So this is our soil layer 3. This is soil layer 2. This is soil layer 1. I'm just going to say top, and then this is soil layer 1 bottom. So this is 1 bottom. So that's why we add this extra layer here. So we have a total stress of 179. Working our way down, total stress. And just like before, But at point A, we're going to have a slight change. Or so what we're going to say, this little point in the center, we need to calculate now. So this alpha, I'm just going to call it alpha, is that midpoint now, because that is where our pore water pressure is going to change. So we need to include a total stress at that point. The total stress is 25.2. And then obviously at the very top, total stress is still 0. Well, remember, keep all those things off to the side. To find our pore water pressure, if it is under the groundwater table, then we have our normal conditions. We have increase in depth, increase of pressure. If it is above our groundwater table, only if we have capillary rise do we have to follow this equation. So since we're told that this degree of saturation is 100%, then this whole thing actually cancels out and it's just negative, right? Because 100 over 100, it's just negative pore water or gamma times the height of water or the height of the capillary rise. So sometimes that's HC, height of capillary rise in it. So to calculate all of this, at D, it's normal, right? At C, it's normal. And at B, it's normal because we're all under or at the groundwater table. And it's not until we go above the groundwater table do we have to add this suction. So we have negative values here. So at alpha, we have this point, but this is directly below alpha. So again, as we're moving up, we have a little point of discontinuity. We have a point directly below alpha where we have suction. And then as soon as we break free of the suction, then it's back to 0. So we have to this little point of discontinuity. So at A to A, we have 0. So above it, we have a 0 kPa. So this is going to cause a little point of discontinuity in our graph. So to plot all of our total stresses are shown there, but then our pore water pressures, again, we have this above and below condition. So that would mean we have different effective stresses above and below that little point. So if we were to actually plot these, that would mean it would look something like this. We have our total stress, which should always be increasing with depth. We have our pore water pressure, which is going to have, you know, we're fine, we're fine, we're fine. And then as soon as we get into the suction area, then we go negative. And then we increase with depth, which means our effective stress, since we are subtracting a negative, we actually have an increase of effective stress in this location. And this is all because of this equation. So if we are subtracting a negative pore water pressure, then we add, and we should see this step forward. All right, sorry I'm going through these kind of fast. Yeah.
Is the A the new top of the water? Like 1.5 here.
This alpha right here, that A?
The top.
That's the, no, this, so this is at 0 here. This is the ground surface. So the groundwater table is still here at B. But now we have, this is the zone of suction. So this is actually 0. So that's why we have the negative.
So what about the? Oh, okay. I thought it was like above the ground.
Okay, no, yeah. There's no ponding, there's no flooding or anything. All right, let's look at another quick example. I got a few more here. This is in a seepage condition. So now we have non-hydrostatic conditions. So at point A, if we were to stick a straw down at point A, what we would see is the total pressure or the height of water would be right here. This would be our height of water. Now at the top at point B, our height of water is right here. So we have 2 heights of water. And if we have a discontinuity in equilibrium, that means we have water that wants to flow from one side to the other, right? So we're going to have water that is wanting to go this way. So we're going to have seepage. So we need to find the effective stress felt at point A and point B. So we know our total stress, that's not changing because it's just one soil condition. So at point A, we have the soil that we're feeling, this 180 pounds. But then we also have 1 foot of this material, and this material is water, so 62.4. pounds per cubic foot is the density. So don't forget to include the ponding or any water that's at the surface or above, the lake or whatever that's above you. Don't forget to include that in the total stress. So think of it as layers. We have this layer of sand with this saturated, and then we have another layer of water on top of it that we still feel the pressure for. So at point B, we only have that water. So we have 1 foot of something that weighs 62.4 pounds per cubic foot. So the pressure is 62.4 pounds per cubic foot there. So that's our total stress. Our pore water pressure is where we need to be careful because we need to see which one we are reading. At point A, then our pore water pressure is the density of water times the height of the water at that point A. So the point A, we don't read this triangle, follow the tube, and we would read this one. So this is for point A. So we'd see 3.5 plus 1 plus 1.2. So that's where the pressure is at point A. So for point B, there's the same equation. We would read the pressure at point B. That's this right here. So our effective stress is, again, just total minus our pore water pressure. So at point A, it's 84.7. And at point B, it is 0. And we have our total stress is equal to our pore water pressure. And that should make sense because think about at point B, what is actually happening is we don't have intergranule connection there, right? Because it's just, there's no soil above us. All right. Sorry, one more. We'll go through this real quick. Actually, there's 2 more, but I'll go through this real quick, just as it's all calculated. So we've already had an example problem like this. This is a heave condition. So we need to find at what depth HS will we have, or at what height, sorry, this should, I guess, should be height of HS will cause heave in the silty clay. So what's the minimum HS where this soil layer is going to be so light that it heaves? The pressure, the pore water pressure is too much that it causes it to heave up. So what we're doing is just talking about statics here. We have the pressure of the water, and then the pressure of the soil is in equilibrium. So if we need everything to be equal to 0 to be happy, if it is greater than 0, then we have uplift conditions. So this means we look for the critical point where our pressure of our water is greater than the pressure from the soil, or the total stress. These are the equations that we follow here. So we can actually set this up into an easy equation we can solve. This means that the H of S, so the height of our soil, needs to be greater than the unit weight of water times the height of the water, or the pressure of the water, which is right here, divided by the density of clay. So this would mean that at this layer, when this is equal to each other, then we have a factor of safety of 1. So let's just say, now using actual problems here in numbers, if the equilibrium is increased to, or sorry, if it is increased to 100 feet in the fine sand, so this is the head, so this is the pressure head of water, what is the HS, so what is the height of the soil that will provide a factor of safety of 3 against soil heave, and we're given the unit weight of soil here. So factor of safety of 3, this means factor of safety, is equal to this from the previous slide. So we can actually solve for the height of soil, including this factor of safety here now. We plug everything in, we're given all the values that we need. This means that as long as our height of our soil is greater than 16.6 feet, then we would have this minimum of factor of safety of 3. If we were to go less than 16.6 feet, then we would have a factor of safety less than 3. So again, this is from the homework problem that I already went over, but what we're talking about here is a pressure, right? And this pressure could be then applied over a length or a width and have an actual finite area. So if we actually needed to find the resulting force that would be needed to anchor this heave layer, then it would just be the stress times the cross-sectional area. And this is like a system that a lot of engineers use, like soil anchors and nailing systems or something like this. Technically, what we're doing is we're calculating a pressure and then installing a point force to resist that pressure, that uniform pressure. All right, one more. We're going to go through really quick. So this is an embankment issue. We've talked already about the importance of embankment, surcharges, all this stuff. This is using Boussinesq's equation. And we're asked to find the increase in vertical stress at point A. So if you notice, point A is off the center of our embankment. So if it was in the center, then we'd be happy and we could easily use that equation. But what we actually have to do now, since it is off center, we need to analyze it as if it was in the middle of the embankment. So what we need to do is we need to recreate a fake embankment by adding on this extra section. And when we do that, then theoretically or hypothetically, we have this half embankment, just a larger embankment. So if we do the analysis for this whole embankment, and I'm just going to call this blue, since it's highlighted in blue, then all we need to do is subtract, once we find all the geometry, then we need to subtract this smaller fake embankment that we added on to it. So once we have the blue and we find the red, we subtract those two from each other and we find the actual increase of the embankment. So the important part with these problems is just finding the correct geometry terms. The B1 is always going to be the flat side. The B2 is going to be the embanked side. So if you have a triangle, then it's only B2. There's no B1. B1 is equal to 0. So there's a figure then that has the nomograph there. You find all these informations for the blue triangle, the blue trapezoid, and the red triangle. You then look at this chart, plugging everything in. Blah, 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 blah. No, make sure you know how to read this chart and estimate it. So we see I2 for the big triangle is about 0.495. For the red triangle, it's about 0.370. So our delta sigma z for our first is going to be here, and we can, since the height is not changing, then we can just move that to the outside of the equation. And we see our delta sigma z is about 165 pounds per square foot. All right, additional stuff. So again, trends of effective stress with groundwater table. Remember, when something increases, how does the stress change? Does it increase? Does it stay the same? I showed that slide like 12 times. So make sure you know those different trends. How to calculate horizontal effective stress, so H, and how to calculate the resulting horizontal pressure, right? So at rest conditions or something. So the equations to find K naught will be given to you, but you need to make sure you apply those equations to determine the pressure profile and then how to find the resulting force. So again, chapter 10, the DOS textbook, that PDF, just make sure you're familiar with what the tables are reading and especially the units. So if you're giving a point load, which table to use? If you're giving a line load, which table to use? I mean, they'll be like, I'm not just going to give you raw tables, like there'll be the description of everything, but just make sure that you're familiar. So if you're doing this, quickly in a test at 7 a.m., you can at least identify, okay, this looks different than what I studied before. And then before the quiz questions, I'll make sure all the quiz questions are unlocked so you can review those too. Any questions on the exam and stuff? Everyone feeling good about the exam?
So are we gonna have to know which table you go to for each?
So the table will say I'll keep the numbers the same, but I'll include this is for point load with whatever,
Corner.
Yeah.
Okay.
Yeah.
And then are we gonna have to remember the M and N values or things like that? You're gonna do
Yep. Yeah. All right, guys, remember 7 a.m. I can't be super lenient. If you sleep in, and I'm sorry, I can't help. Just start waking up early. We have finals week. We're on a tight schedule. I will bring in coffee and maybe donuts. We'll see. But yeah, the practice problems will be posted, solutions posted over the weekend. Good luck, guys. Enjoy your last week of classes and last weekend before summer.
Are the videos still recorded?
Yep. Yeah.
Yeah.
Yeah, no, they should all be posted. I'll post this like right after whenever it's done. Stuff. What's up?
So in the fall, I plan on continuing with the way scheduling and stuff lays out. Your class like lands right in the middle of the day.